Welcome back to More Fun with Finance. I'm Dr. William Elliott and coming to you from Uptown Shaker Heights. So we're going to continue that review that we started last time from Chapter 3. This time we're moving into Chapter 4, and we're going to be talking predominantly about the concepts related to time value of money. Really, I can't emphasize how important this topic is. If you understand nothing once you get out of this class other than time value of money, you will have gotten a large chunk of what finance is really about. So we're going to go back through and review some of these concepts that you learned in your introductory finance classes, and hopefully this will help you as you move through this class, because we're going to take that information and kind of leverage all of that. So without any further ado, let me switch over to the slides. I will get out of the way here momentarily. There we are. And okay, so we're going to be talking about one period as well as multi-period time value of money. We're going to be talking about compounding. We're going to be looking at perpetuities and annuities, as well as just a brief foray into amortization. So here we go. By the way, I also wanted to mention I'll be using the calculator as well as some spreadsheets here. So I'll show you how to use both, and that way it'll be flexible. If you're not near a computer, having a calculator is pretty darned handy. You can do some pretty powerful things with a financial calculator. All right. So one period case, here's an example. Suppose that we're going to invest $10,000 at a rate of 12% a year for 1 year. We expect our investment to grow to $11,200. Now that $1,200 of interest is gotten to by taking the principal, the $10,000, times the 12%, or in decimal form, that would be 0.12. Add that interest to the principal, because hopefully we're getting the principal back, and we will have the answer of $11,200. So this is a relatively simple calculation. This is what's known as a future value. So we're going to be assuming, let me show you this on the blackboard. I like to use a timeline. Timelines are really helpful. And so if we start over here with our $10,000, and we're going to be earning 12%, or 0.12 over this period of time. So we're moving that $10,000 out to time 1, the end of the year. So we get our principal back, plus we get that $1,200 of interest. So we have $11,200 at the end of that period. So hopefully that's pretty simple, pretty basic. Let's jump over to the camera here, and let me get that going. Hopefully this will work. Yes, it will. So here we are with our calculator. I'm going to clear that. And so we have one period. So I'm going to enter 1 for the N. And then I'm going to enter 12% for the interest. And I'm going to enter a 0 for the payment because we don't have any other payments. I'm going to enter 10,000 for the present value. And then I'm going to compute the future value. There's our 11,200. And of course, the negative sign out in front of that just tells us if we had $10,000 coming in, say this was a loan at 12%, then we would have to pay back the 10,000 plus the 1,200, or a total of 11,200. We can just flip the signs on it. If we're lending $10,000, then that would be a negative cash outflow, and then the cash inflow would be a positive $11,200. All right, so good enough on that. Now, let's get back to the slides. Here's the formula in a more generalized form. So no matter what the present value is, this is what we were talking about with the 10,000. That would be our PV. The 0.12 or 12% would be our R. And then the future value would be the 11,200 in the example that we just worked. So, and obviously, you can think of that 1 there. That's carrying the principal forward. All right. Now, we can also reverse this and come up with what a present value is. A future value is known. We want to figure out what a present value is. We just move things around in this equation. And we have something like this. So if you were to be promised $11,424 due in 1 year, when interest rates are at 12%, your investment would be worth $10,200 in today's dollars. You put that equal sign in there. All right, so this is the future value. This is 1 plus R. That is 1 plus R 0.12. And then, of course, this would be the PV. So this is future value, and then this is 1 plus R. All right? And we can see this again in a more generalized formula. This C1, we could have written that as future value. But in this case, the authors chose to just recognize it as some cash flow at time 1, as opposed to the future value. But here is that same thing right down here in the corner. All right. Now, we come to this concept of net present value. So net present value, we've been talking about present values and future values. This is net present value, or NPV, a very, very important concept, and we'll be coming back to this frequently over the semester. In fact, when we get to chapter 6, we've got an extensive problem that the end result is an NPV. But NPVs basically take into account the cost of the investment. So we're going to be looking at, we're usually going to set it up where we have some sort of cost at the outset. That would be a cash outflow. It could be an investment in a savings account. It could be into a money market, a stock. It could even be into some sort of corporate project. And then that investment is going to generate cash inflows in the future. And we're going to discount those back to today at the discount rate, that R that we were looking at. And then we're going to add all of those up, subtract off that initial investment. And if the NPV is greater than 0, then we have an investment that is one that we would undertake. If it happens to be less than 0, then we don't take the investment. All right? So in this particular case, suppose that an investment promises to pay $10,000 in 1 year, and it's offered to us to be purchased for $9,500. We're assuming an R, or an interest rate, of 5%. Should we buy this investment? I'm going to give you a second. Grab your calculators, grab a spreadsheet, whatever you have handy, take a look at it, and see what you think. All right, we're back. Did you get $23.81? If you did everything correctly. So let's walk through this. We start off with our cost, $9,500. And then here is the cash flow that we'll receive. And at 5% for 1 period, that turns out to have a present value of $9,523.81. So subtract from that the original cost of $9,500, and we have a positive NPV of $23.81. All right. Pretty simple. A lot of what we're going to be doing in this class is like this, but just with a whole bunch of other additional details added in there, like salvage values, depreciation has to be accounted for because it's a non-cash expense. We have to deal with that. We have to talk about how to deal with interest rates, or excuse me, interest expenses, things of that nature. But at the heart of many of these problems that we're going to be working on this semester, it boils down right to something like this. So always keep that in mind when you're working on these much more complicated problems, that you did do this one and everything else is just some variation on it with an additional complication or 3 or 4 or 5. All right? So let's keep going on with this. A more generalized form would be what we see right here, where NPV is equal to the cash outflow, the original cash outflow. Usually we look at that as occurring at time 0, so that doesn't have to be discounted. But sometimes if we have additional expenses further out in time, we still have to deal with that, but we can net that out from the cash inflows as well. And then we've got the present value of all the future cash flows. Multi-period future value or present value. First, we'll talk about the future value. Here, all we have to deal with is we're looking at the t superscript or the exponent up there. How many periods out is that cash flow? So we can certainly we can take a present value and we can gross it up for t periods. So if we have some amount and we want to invest it for 1, 2, 3 periods, then we're going to be looking at a future value 3 periods from now. R is always stated in this period, whatever that is. It could be a month, 6 months, a quarter, a year, and then we just count the number of periods. So our t in this case would be equal to 3. So again, it's very basic. We could just do this manually. We could take it back 1 period at R, and then another period at R, and another period at R. But we end up with the same thing if we use this handy dandy formula right here. Let me just clear that off so that you don't have to see it with all my scratch on there. All right, so that's what we do for a multi-period case. If we want an example of this, suppose that we have a stock currently paying a dividend of $1.10, which is expected to grow at 40% per year for the next 5 years. What's the dividend going to be at the end of year 5? All right, so present value would be that $1.10. T is 5 periods. And again, if you have any doubts, always just timeline it out. 1, 2, 3, 4, 5. So 1, 2, 3, 4, and 5. And so we start with $1.10 here. We go out 1, 2, 3, 4, 5. We're looking for that future value out here. So what is that? Well, we take $1.10 times 1 plus r raised to the 5th power. That turns out to be $5.92. That's the beauty of compounding, right? If we didn't compound, for instance, if we just got 40% on $1.10 each period for 5 periods, that's what we're doing here, that would only end up being $3.30. But that is not correct. That is wrong. So don't do it that way. Let me put it in a slightly different frame. That first $1.10 that we have as a dividend, then we increase it by 40%, and we get $1.54. So that's $1.10 times 1.4 is $1.54. So that's an extra 44 cents on there. All right. Now, The next time we do this, we're going to take the $1.54 and increase that by 40%. So we're not getting another 44 cents. We're getting more than 44 cents because we don't have $1.10 anymore. We're starting from a base or a principal of $1.54. So whatever that turns out to be, we have $1.54 times 1.4 is $2 and not quite 16 cents. All right. So we're getting extra money. We're getting that, not just that 44 cents. We're getting an additional, 61 cents, I believe. What is that difference? Minus $1.54. Yeah, 61.5, 62 cents approximately. And we continue iterating that way. All right. Now, another thing to look at, they just show you a slightly different version of this. They show you all the dividends. So starting at $1.10 and then increasing by 40% becomes $1.54. If we increase that $1.54 by 40%, we get our $2.16. If we increase that $2.16 by 40%, we get $3.02. So that incremental increase in terms of dollar amounts becomes larger and larger and larger. It's still 40%, but it's 40% of a higher base each time. That's compounding. That is really valuable, especially if you have a very long time frame. Think about retirement. You've got 35, 40 years to do that compounding. That's that's really powerful. All right. Here we've got getting a present value, and we know that we need $20,000 5 years from now. We're going to be able to invest at 15%. We want to know how much money do we put in today to have that 20,000. Well, 20,000 divided by 1.15 raised to the fifth. All right, that's that 1 plus r raised to t. All right, so we're going to bring it back 5 periods, and the amount that we earn on that is $9,943. Finding the number of periods. Sorry, let me clear that marking off of here. That one gets a little trickier. T and finding R, which is the last thing we're going to do, they're a little trickier because of the algebra. Let me give you, though, a bit of a shortcut here on this one. There's a thing called the rule of 72. So if you take 72 divided by r, you get an approximation, and I should do this with squiggles because that means approximately. You get an approximation of the number of years. So in our case, 72 divided by 10% is 7.2 years. Notice we've already got the solution here. It's really darn close. Is it close enough? Maybe, maybe not. Depends on your purposes. But the rule of 72 is a handy, back of the envelope thing. You can do it in your head if the rates are relatively easy, like this 10%. Just move the decimal over. And so that's a really handy thing to have. Clear these off, though. So let's walk through the algebra here just briefly, though. Here's the present value. Here's the future value. This is the present value here. And then here's 1 plus r raised to the t. And we know everything except for the t. We're solving for t. So let's try to isolate this guy over by itself. So we'll divide both sides by 5,000. And so we end up with something like this. And since 10 over 5 is 2, let's simplify that. So now we have 1.1 raised to the t equals 2. Now we have to deal with the exponent. I don't know if you recall this, but think back to your algebra, and you probably learned at one point there's a property of the natural log that basically says the natural log of some value raised to some power is equal to that power times the natural log of that variable. So we're going to take advantage of that handy dandy little property, and we're going to move that exponent down to down out of the superscript, basically. So we could write it this way. All right, if we take the log, and whenever we take a natural log, we got to do it at both sides, right? Otherwise, it would ruin the equality. So we have the natural log of 2 is equal to the natural log of 1.1 raised to the t. Now let's rewrite that left-hand side. So that would be t times the natural log of 1.10 is equal to the natural log of 2. Now we divide both sides by the natural log of 1.1, and over here too. This cancels out this, and we're left with t by itself over on the left-hand side, and then we've got this, which is right there. All right? Now, plug in your calculator 2 and hit the ln key for natural log, and you'll get 0.6931. Plug in 1.1, hit the natural log or the ln key, and you'll get 0.0953. 0.69 divided by 0.095 is equal to 7.27 years. And there you have your number of periods to get from $5,000 to $10,000. And then finally, sorry, I've got these markings on here. Finally, we want to look for a rate. So we're solving for R in this case. And here's the example. We want to have $50,000 for our child's education. We're going to deposit $5,000 today, and we need the $50,000 in 12 years. What rate do we need to earn to have the $50,000 if we're only depositing $5,000 today? That's quite a heavy lift, as we're going to see, because here they give away the answer. It actually turns out to be a little over 21%. How do I get to that answer? Well, again, more algebraic gymnastics. So we've got 1 plus r raised to the 12th here. We want to isolate it by itself, so let's divide both sides by 5,000. We end up with this. That simplifies to 10. So let's take that. So we have 1 plus r raised to the 12th is equal to 10. Now, one other property that we can do is take the root of something, and in this case it's the 12th root, to get rid of that 12 exponent on the left-hand side. So if we take the 12th root of both sides, and by the way, this radical that you see, you could write it as that, or you can write the 12th root as 1 over 12, the exponent, right? So we're going to write it this way. So if we take the 12th root of this, that's 12 over 12, that becomes 1. So that exponent goes away. And then we're just left over here on the left-hand side with 10 raised to the 12th root. The easiest way to deal with this in the calculator is to figure out what is 1 over 12, and that turns out to be 0.08333333. And then we can use the y to the x function in the calculator. So we'd plug in 10, hit the y to the x button, and then type in 0.08333. And you will end up with a value of 1.2115. Now we still have to subtract that 1 from there, and we're left with 0.2115, which is the decimal equivalent of 21.15, right up here. All right? We're done with the algebraic gymnastics, but it's always a good thing to kind of practice that stuff. Calculator keys, I suspect you probably know that. You don't really need a review of that. But if you do, here they all are. Oh, don't forget that N. Now, let's look at multiple cash flows that have different values in each period. All right. So here in this example, we're going to start off with $200 1 year from now. And every subsequent year for the next 3 years after that, it's going to grow by $200. So here's the layout. Year 1, 200. Year 2, 400. 200 plus 4. Or sorry, 200 plus 200. Year 3, 400 plus 200, so 600. Year 4, 600 plus 200, 800. All right. Now, we could do this individually. So we could take the present value, we could find the present value of a future cash flow of $200 1 year from now. We're going to use, I believe, 12%. Yes, there it is, 12%. If we do that calculation, it turns out that the present value of that $200 1 year from now at a discount rate of 12% is $178.57. All right. Do the same thing for 4, 6, 8, and we come up with these numbers respectively. Now we add them all up, and I just overrode on my answer here, but there's our answer. $1,432.93. I can zoom in on that. All right. That's the present value of all those future cash flows. Now, one other thing that we're told in this problem is that we're able to buy those cash flows for the reasonable sum of $1,500. Should we do that? If we believe that 12% is the right rate and we believe that all those cash flows are going to reveal themselves, the answer is no. Because all those cash flows should actually be selling for $1,432.93, not $1,500. All right? So those are multiple cash flows with different cash flows in each period. Now, you might ask, how do I do that on my calculator? Good question. And I'm getting an ad. All right. Give us a second here, and hopefully that ad will disappear. There we go. All right, let's clear this out and get back to our cash flows. I've actually already entered these in here, but just follow along with me. So the first step is to hit that cash flow button like I just did, and this is what you see, CF0, cash flow times 0. We know that that cash flow is negative $1,500 because we would be paying for this and then we would receive the future cash flows. But I'm going to leave that out for the moment. I'm just going to leave it at 0. So effectively what we're doing is not a net present value here. We're just getting a present value of uneven cash flows in the future. Now, down arrow in this upper row once, and I get cash flow 1. Now, I had already entered this. I hadn't cleared the register, but to enter it, you just go 200. And here's one of the tricks. I know people who forget this. Sometimes I've done it myself even. You got to hit the enter key. Don't forget that enter key. Now, down arrow once more. And we get this F01. That stands for frequency. So what the calculator is trying to do is it's saying, hey, are you seeing this cash flow just once? Or are you seeing it multiple years in a row at $200? And in our case, we're just seeing it once, so we accept a default of 1. We go down arrow. I've already entered the 400, so let's down arrow that, and it's 1 period. 600, 1 period. 800, 1 period. And we don't have any more cash flows, so cash flow 5 is 0. Now, the next trick that always is weird, I don't understand why they did it this way, but they did. We're stuck with it. The next thing you do is you hit the NPV button. It brings up I. Well, I is the rate that we want all of these cash flows to be discounted at. In our case, we're talking about 12%. And again, don't forget, hit the enter key. All right. Now we hit the down arrow one more time. Now we get to NPV, but it says 0. Oh, one more keystroke that I need. I've got to hit the compute key, the CPT at the very upper left. When I hit that, Now I get my $1,432.93 and a little bit of change on the side there too. All right, so if you want to do it on your calculator, that's the way to do it. Let's get back to our slides. All right. And here's the example. They're showing you how to do this on this slide using the calculator. All right, so compounding within a year. I like to use whatever period is being used. If it's 6 months, I set everything at 6 months. If it's a quarter, I set everything at 3 months a quarter. If it's a month, everything at a monthly rate. And what I do is let's say that we're doing semi-annually. So to get semi-annual R is always stated in annual terms, per annum. All right, per annum means annual. If you see that word, that means it's stated in annual terms. All right, so per annum, to get it 6 months, divide that by 2. To get my T is assumed to be in years, but I've got 2 periods every year, so it's actually, in this case, T times 2. So if I've got T years, I've got now 2 T years if my compounding period is every 6 months. You can follow the book's notation here. They've switched to M to recognize that it's not annual anymore. And here they divide by M, and up here you raise it to the mth power. But the problem is that what they don't tell you is that it should actually say M times T. Anyway, deal with it however you like. Like I say, my preference is to do all of the work up front, adjust the rate to the period, and adjust the number of periods to what is correct for our compounding. In this example, if that's not quite clear, which I don't even think I think it's quite clear. Let's work an example. That always proves the point. So let's say we invest $50 for 3 years at 12% compounded semi-annually every 6 months. All right. So we're going to divide the R by 2. So on a semi-annual basis, 12% per annum is 6% per semi-annual. And then we're going to increase that 3 years by 2. We're going to multiply that by 2. So it's 6 periods, right? We've got 1, 2, 3. And since it's semi-annual, we split each of those. So now we have 1, 2, 3, 4, 5, 6 periods. So now our exponent is 6, our rate is 6, and $50 times 1.06 raised to the 6th is $70.93. Hopefully that clarifies anything that wasn't crystal clear when I was just discussing it in a more abstract setting. We can figure out what the effective annual rate is of anything by kind of reverse engineering this. So in this case, the effective annual rate of interest is the annual rate that would give us the same end of investment wealth after 3 years. And it turns out that when we do that math, we've got future value, we've got the present value, we're solving for this. We know this is number of years now. And what it says here is that effective annual rate, when we're compounding semi-annually, is over 12. You might ask, well, wait a minute, why is that? Well, remember, if we just go one period, and we only compound that one period at 12%, $1 becomes $1.12. But if we split that into 2 6-month periods where the rate is 6% each of those periods, then we get the first period, we get $1. We start with our $1. And let me clear this off, clean up things here a little bit. 0. This is the 6 month. This is 1 year. We're going to start off with our $1 here. We're going to go at 6%. So our $1 becomes $1.06. But, and that there's nothing magic there. The next period, now we're starting with $1.06, and we're earning still that 6% interest on it. So come to the calculator, and we take our $1.06 times 1.06, and we end up with $1.1236. So that extra 0.36 cents, that's because we're earning interest on the interest we earned in that first 6-month period. And that's why this effective annual rate, even though the nominal, remember, we started out here by saying it's 12%, right? But because we're earning interest on our interest within a year, and we're getting that little bit extra, now our effective rate is now a little over 12 1/3%. Again, effective annual rates are really super important. And so if you have any questions about that, feel free, drop a note into the discussion forum, and I will try to answer a question. All right? Here, let's see. This is on a monthly basis. Same idea. We've got an 18% rate, but we're compounding monthly. So we divide the rate by 12 because there are 12 months in a year. We multiply the year, and here we're just assuming 1 year. We multiply that 1 by 12 because there are 12 months in a year. So our exponent becomes 12, and we end up with 1.015, that's 1.5% every month, raised to the 12th power, gives us 1.1956. We need to subtract the 1 off of that, actually, to get 0.1956, or 19.56%, which is over 1.5% higher than that nominal stated rate that we started with up here. And again, this idea of compounding is really important. One last thing on compounding. Let's not just do it semi-annually or quarterly or monthly or daily. Let's do it in continuous time. So we've shrunk that time period down to an infinitesimally small time period. Continuous time compounding. How do we do that? Well, we've got to bring out this handy-dandy exponential, this e, where e is 2.718. All right, there's a calculator key for that, so don't worry about it. You don't have to know the details behind it. You just have to know to use it. And what we're doing is we're raising that e to the RT power. All right. R being our interest rate, and that's stated in nominal terms, in annual terms. And then T being the number of years. All right? And then we multiply that result by the cash flow, and we have a future value. Okay? Now, on to something a little different. There are several different types of cash flows that we encounter regularly. One of them is called a perpetuity, and another is called an annuity. And they are both very related to one another. A annuity is a series of cash flows where each cash flow is the same and they're separated by exactly the same time period. But they have an end period. They have an end point. So I might have an annuity that pays $1,000 a year for 10 years. A perpetuity takes that annuity and it says, let's not have an end period. Let's just run it out to forever. So I get $1,000 a year forever. All right. So a perpetuity is simply an annuity where the payment is going on out to infinity. Then your authors also talk about a growing perpetuity and a growing annuity. Instead of having a constant cash flow every period, a growing annuity and a growing perpetuity have the cash flow growing at a constant rate over that time span. We run into these quite frequently, like I said, so there are some simplifications about how to deal with them. We're going to look at those just momentarily. So let's start with just a regular old fashioned perpetuity. Now, a perpetuity is, remember that cash flow goes out to forever, infinity. So we can't even calculate it, in a practical sense. Now, what we can do, though, is we can understand that the further out we go, these exponents get bigger and bigger and bigger and bigger, and this cash flow stays the same. It's the same amount. And so you know what an exponential function looks like. It goes like this, right? It's not linear, it's curvilinear. And so it doesn't take getting too far out here before that cash flow, or that discount rate factor, or that discount factor, I should say, gets really big. And it means that the present value of those future cash flows beyond about year 25 become meaningless. They're really, really, really small. Since they become so small, we can pretty much ignore those that are way out here in the future. Certainly by the time we reach year 40 or 50, definitely year 100, they just become tiny. And it turns out that using a Taylor series expansion, we can do a little bit of math, and we can find out that we can actually estimate that value by simply dividing the cash flow by the discount rate. C divided by R. Nothing difficult. Here's an example. Suppose we have a perpetuity that pays 15 pounds sterling every period forever. And suppose that the interest rate on that is 10%. So it's 15 pounds sterling divided by 0.1. So the present value of that is 150 pounds sterling. Now, you could practice this. You could say, well, let me take 15 pounds sterling and discount it one period at 10%. Let me do another 15 for 2 periods, another 15 for 3 periods, and do that until you get out to about 20. Now, I wouldn't want to do that on the calculator, but you can very easily do that in a spreadsheet. And you can prove to yourself that the value that you get out of those discounted cash flows approaches 150. And the further out you go, the closer you get to 150. Presumably at infinity, you've actually reached 150 in the limit. All right? Now, let's grow that perpetuity. Let's say that it grows at a rate of G every period. Whatever G is, doesn't matter. So here we have cash flow starting out at the stated rate, and then the next one grows at the rate of G for one period. And then the one after that grows at the rate of G for 2 periods, 3 periods, 4 periods, and so on, forever. We're still discounting at R for the appropriate number of periods. And again, there's a bunch of math. There are algebraic proofs behind this. You can do a numerical proof yourself with a computer and a spreadsheet, and I recommend that you try this just to make sure that it makes sense to you. If you were to set this up in your spreadsheet and have a column of C and then grow it by G for 1 period, 2 periods, so on, and run that out like 100 years worth of that, discounted at some rate R, you would see that the value that you get when you sum all of those up asymptotically approaches the value that you get when you use this handy dandy simplified formula right here. We're just taking C and dividing it by not just R, because that was the perpetuity, but R minus G. We do have to assume that G is less than R. Otherwise, this doesn't work. But as long as that's true, then we can get a closed form solution to an infinite series without any algebra, well, without too much algebra. All right? Okay. Here's an example of that. We're going to grow this at 5%. We've got a discount rate of 10%. We start off with $1.30, and that is worth $26. Easy peasy. Check the math. Maybe use this example, plug this into your spreadsheet, run it out for 100 years, grow that $1.30 at 5%, and then discount that result by 10% for the same number of periods. Sum all of those present values up, all 100 of them, and see how close to 26 it gets. I'll bet you it will be within a penny or less. It'll be $25.99 and some change. Let's go on to an annuity. Remember, an annuity is just a perpetuity that has an end point. But if that end point is way the heck out there, they're almost the same value. I'm not going to go into the algebra here. Just note that here we have the same thing that we started with for the perpetuity, right? Also notice that within these brackets, it's saying 1 minus this thing here, this fraction. So if I were to write this out, if I were to do this multiplication, remove the bracket, so I would have C over R minus C over R times C over 1 plus R raised to the teeth power. So basically what's happening here, oh, sorry, I'm in the way. What is happening here is that I'm saying the value of that annuity, let me write a timeline out here. And let's say this is the end point of the annuity. All right? So and this is time 0. Now, this C over R, that gives us the value all the way out to infinity. This little doodad here, again, I'm in your way, but there it is. That guy subtracts from that value the amount beyond the end of the annuity. What we're left with is the value just up to the end of the annuity. So if you think about it conceptually, let's not worry about the algebra behind it. Just think about that conceptually. That's what's going on in this handy-dandy little shortcut, simplified formula. And again, you could do this on a spreadsheet. Now because we're not going out to infinity, you could actually do this in a spreadsheet and get the exact same answer. But, even if it's, on a spreadsheet, this is still a little bit easier to do. Here's an example. I'm not going to bore you with walking through this. I'll leave it to you to take a look at it and um, make sure that you can, do the math. All right. This one is actually a monthly car payment. So notice that they're giving you a per annum rate. You have to put that on a monthly basis. That's why they're dividing that by 12 down here. That's also why they're multiplying the 3 years by 12 to get 36 periods. All right. Same thing down here. But other than that, it's exactly that formula that we just looked at on the prior slide. And then let's go on to a growing annuity. Surprise, surprise. Same little trick, same little hat trick. The fraction that we have over here is a little different, but here is that value of a growing perpetuity. Here's the 1, so that's the value of the entire thing out to infinity. And then subtract from it the part beyond the end of the annuity, and you have just that period over which you get the growing annuity. All right? We're almost there. And again, I'm not going to bore you with the example, but work through that yourself just so you're comfortable with it. And finally, almost to the end of chapter 4 here, loan amortization. So we can amortize loans in a variety of different ways. The one that you and I are most familiar with is a amortized car loan, an amortized mortgage on a house. And that's where we have a constant payment that's composed of both principal and interest. And at the end of that loan, we will have paid off all of the interest and all of the principal. So you might have a 30-year amortized loan and you pay X dollars every month. And at the end of those 360 periods, you will have paid not only the interest, but all of the principal as well. And in fact, an amortized loan of that length, of that term, you pay a heck of a lot of interest, a whole lot of interest. So try to avoid that in your personal life. Just a little tip. Those things, yeah, you can afford a whole lot of house, quote unquote, but you could actually save a whole lot of money by doing it on a 15-year basis. I mean, we're talking hundreds of thousands of dollars probably that you would save. So think about it. Now, there are other types of amortized loans too. A pure discount loan even falls into that category where we borrow $1,000 and then at the end of the term we have to pay back $1,000 plus whatever the interest is on that loan. Here's an example of a discounted loan, a pure discount loan, and that's usually the case on something like a T-bill. Government doesn't want to have to mess with everything on a monthly basis or pay coupons out. So what they say is, look, you pay me $9,345.79 right now, and then 12 months later, we're going to pay you back $10,000. And by the way we've calculated this, we know that that actually is going to yield 7%. 7% on our $9,345.79. So if you were to take 93.4579 times 1.07 raised to the 1, because it's 1 year, you would get exactly $10,000. Okay? Easy peasy. There are other types of loans that may only have interest payments. So most of these are for corporations. You and I don't run into too many of these, but corporations do quite frequently. So you borrow $10,000 at 7%, and then every year you just pay $700. That's the interest on the $10,000. Next year you pay $700. The next year you pay $700. Whenever you want to pay off the loan, you pay that final interest payment plus the $10,000 principal. Okay, that's an interest-only loan. I'm not going to go through these in any great detail. I'll leave it to you to take a look at it. Here's an amortized loan with a fixed principal payment. And again, that's not the type of amortization that you and I see on a car loan or a typical home loan, but again, corporations experience these. So the principal payment is constant. Notice that's over here, $5,000 every period. We started with a loan of $50,000, and every period we pay back $5 for 10 periods until we pay back all the principal. Now, the interesting thing about this is that the interest payment on that loan drops every period because we're paying back part of a large chunk of principal, right? So we start off with an interest payment of $4,000, and then it drops to $3,600, and then it drops to $32,000, and then it drops to $28,000, and so on down the line. All right? And I don't think, when I'm looking at this slide, total payment does not look correct to me. Not sure what they're doing here. If I were to rewrite this column, I think there's an error in this column. This should be 9,000, right? Because it's 4,000 plus 5. This next one should be 8,600. This next one should be 8,200, and so on. Not sure, unless I'm misreading that column, but that doesn't look right. And then here's an amortized loan that you and I are familiar with, and that's where we have a fixed payment, but the principal payment varies over time. The amount that's principal versus interest changes over time. And you'll notice here that the principal is always a smaller part of the payment in the near term than it is in the future. And that's why when you go out on a 30-year monthly mortgage, that first principal payment is just tiny. So you're just barely paying back any of that money. And it takes 10 years before you're paying back any sizable chunk of principal. So most of your payment in those first 10 years is interest on whatever you borrowed. And then you're just barely whittling away on that principal. All right, I think that's about it for this chapter. And I look forward to seeing you next time for Chapter 5. Have a good evening. Bye-bye.